So today we want to take this semicircle and describe it in three different ways that we're familiar with a function, with an equation plus some kind of restriction, and then with a parameterization. And then we want to use each of those descriptions to get at the equation of a line tangent to the function at this given point, -3/2 and 3√3/2. So here are our three descriptions in reverse order. First, I've got the parameterization. We weren't told what parameter, any kind of restriction on the parameter, so we're just going to use whatever parameter occurs to us first. This is one of our standard parameterizations of a circle, where x is cosine and y is sine, and t goes from 0 to 2 pi. This will start off at the positive x-axis and go once around counterclockwise. If we want to adjust the radius, we adjust the amplitude of our cosine and sine. And since we only want the top half of the circle, we'll parameterize from 0 to pi. For our equation, we know the equation of a circle is x squared plus y squared equals r squared. So we're just going to have x squared plus y squared equals 9. For Desmos, if I just want to display the top half of the circle, I'm just going to tell Desmos in curly brackets, make sure that y is greater than or equal to 0. Don't use the negative values of y. And at which point Desmos is like, oh, why didn't you just write it as a function? And then the next thing I did was write it as a function, where we just solve the equation for y. Y is equal to plus or minus the square root of 9 minus x squared. And since I want the top half, I just care about the positive square root. So I leave off the plus or minus and just take the square root of 9 minus x squared. And they're all the same. So if we turn them all on, so oops. The next thing is to take each of those descriptions and use each description to find the equation of a line tangent to a function to the curve at the specified point. Let's start with our function. We were trying to find the equation of a line. That means we need a point and a slope. The point has been specified, and the line is tangent to a curve. So therefore, we're going to use the derivative. So if f of x is the square root of 9 minus x squared, which we're going to write as 9 minus x squared to the 1/2 power, the slope is going to be from the derivative. We're going to need f prime of x. The derivative of something to the 1/2 power is 1/2 of that thing to the negative 1/2 power times the derivative of that thing. So the 2's will cancel out. And we'll end up with a negative x over the square root of 9 minus x squared. Now our f prime of x is purely a function of x. So the only part of the point that we need is the x part of it, the -3/2. So x is the -3/2. So the slope that we want is just f prime evaluated at -3/2. Kind of a negative minefield. So on the top, I have the negatives cancel out. So I'll just have 3/2, and I'll have on the bottom 9 minus, let's see, a -3/2 squared is -9/4. So down here I'll have 9 minus, the negative gets squared. 9 minus 9/4. The negatives cancel, so I'll have 3/2. 4 times 9 is what, 36? Yeah, so it's 36/4 minus 9/4. Oh, now I have to do 36 minus 9 is what, 27? It's the square root as well. So we're going to multiply by the reciprocal of the square root of this. So it's going to be what, 2 over root 27. So the 2's cancel. Square root of 27 is 3 root 3. So the 3's cancel. And the fact that at an angle of 2 pi over 3, we ended up with a 1 over root 3 should make us immediately suspicious. Oh, yo, isn't that the tangent of 60? Is it? And it is not, because it's positive, and we're clearly in the second quadrant where tangent is negative. But now I've got a point, I've got a slope. With that, we can write the equation of a line. Now, I'm not going to write this in slope-intercept form, because that would require calculation. I would have to multiply some stuff out. So forget that nonsense. I'm just going to write it in point-slope form. So y equals, let's see, y starts off at 3 root 3 over 2, has a slope. This is messy. This one's all rationalized, so I'm going to rationalize this one as well. Plus the slope root 3 over 3 times x minus the x coordinate negative 3/2. No problem. How's everybody okay? Right. I asked you to, we started with a function and we said find the equation of a line tangent to the function at a given point. We take the derivative so that we can find the slope. Plug in the x coordinate of the point, and there is our equation. No problem. There's a little bit of algebra. I was doing some arithmetic, which is kind of sketchy, but seemed to work out okay. I can think that is the correct answer. Let's find out by doing the problem a couple more times. So if we have the equation x squared plus y squared equals 9, and this is only for y greater than or equal to 0 for the non-negative values of y. We want to find the equation of a line tangent to this curve at a given point. The point is already available, negative 3/2 and 3 root 3 over 2. But we need the slope. For the slope, we need dy dx. Since our equation is not written in a function form, we can use implicit differentiation to get at dy dx. So I'm going to use implicit differentiation for this one. Because our equation is not in the form of a function, it's in just an equation involving x and y, even though it's not hard to find the equation, to find a function for the curve that we want, we're still going to use implicit differentiation because that's what we're looking at, an equation where everything's mixed up. So the derivative of 2x with respect to x is, sorry, the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is the derivative with respect to y, so plus 2y, times the derivative of y with respect to x. And the derivative of 9 is 0. So we used implicit differentiation. The 2y is the derivative with respect to y. The chain rule says multiply by the derivative of y with respect to x. Yeah. Ric Flair loves the chain rule. Woo. What we're looking for is dy dx. So I'm going to solve this equation for dy dx. So this tells us that dy dx. I'll subtract the 2x from both sides and divide by 2y. The 2's will cancel and we'll get negative x over y. Now for the slope, we just need to plug in our point xy. I want dy dx evaluated at the point. So the slope is dy dx evaluated at the point. Negative 3/2, 3 root 3 over 2. So minus 3/2, oh, a negative 3/2 over positive 3 root 3 over 2. The negatives cancel. The 1/2 cancels. The 3's cancel, and we're left with the same thing, 1 over root 3. Since I had rationalized the 3 root 3 over 2, I should take my slope, I should rationalize that as well. So instead of 1 over root 3, I will write it as root 3 over 3 so that it fits in with the rest of the end. It would be really awful to write a decimal for this and then mix that with all your fractions and then mix a decimal that's been rounded off with some fractions that have radicals in them. That would just look awful. Pick one and run with it. Some people do decimal approximations, just leave pi hanging out. They're like, oh, 10.567 pi. I take off 1,000 points for that. That's just unacceptable. Why approximate that and not incorporate pi into it? You know what I mean? That's just weird. So unsurprisingly, we got the same slope that we had before. And you may be thinking, wait a second, this 1 over root 3, I'm sure this is some kind of tangent business, isn't it? And it's not quite tangent business because look at our derivative. It's x over y. What is x? X is cosine, y is sine. So it's not tangent. It looks like it's cotangent. Any questions? This leads to the same equation because I just found the same slope that I wanted. So. In the third part, we've got a parameterized curve. So now we're going to have to do some different stuff. Now there's going to be some different things going on. So let's take a look at what we got. So once again, we want to find the equation of a line tangent to this curve that's now been parameterized at a given point. We're trying to find the equation of a line, so we need a slope and a point. The point has been given to us. The slope we're going to find with derivatives because this is Calc 1, and also because I said tangent line. Tangent line should make you think slope. Slope should make you think derivative. The difficulty that we run into with this problem is that our equation is parameterized. So when we start looking at derivatives, I have x of t is 3 cosine of t. Now we could take derivatives of this, but this is not going to be the derivative of y with respect to x. This is the derivative of x with respect to t. Rather than writing x prime, we're going to note that we get a different set of derivatives. So the derivative of 3 cosine t, derivative of cosine is negative sine. So negative 3 sine of t. But that's not dx, dy dx, that's dx dt. Now, y of t is 3 sine of t. We could take the derivative there, which we should, because we're playing the equation of the tangent line game. We need the slope, but the slope is dy dx, and our derivative here is dy dt. Derivative of sine is cosine. So we take the derivatives like normal. Was that? Oh, dx dx. My t fell over. Ct is like an x, but it fell over. This is what happens when you drop out of engineering school and go to math school. You don't properly support your variables, and so they fall over. Because I didn't write the t, I wrote it more vertical. I didn't stick it into the ground enough. So it's kind of like boop. This way, you bend the bottom out a little bit. That gives a little flat surface to sit on. It might roll over, but as long as I don't hit the paper too hard going this way, it won't slide out. So we're good. So the difficulty that we have now is that we need to find dy dx. That's what the slope is. Slope is dy dx. But we have dx dt and dy dt. We need to get the slope as dy over dx. How do we get that slope? So all we have to do is, oh, look at the time. I guess we'll have to figure this out tomorrow. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day and thanks. Bye.